Alrighty, talking about 3.12, the photoelectric effect, one of my favorite because this is, I think, almost our last equation. Wait, no, we have 3.13. So the photoelectric effect, what is it? It's if you shine a light on something, you can have electrons leave the substance, right? If it's an atom or a molecule, you shine a light on something, you can pop electrons off. Now it has to be just the right kind of light, but this is why you can heat up, like part of your grill, right? You've got metal parts on a grill outside, and when you heat it up, they're black initially, and now they're like glowing red. That's the photoelectric effect. Okay. So one of the main equations we're dealing with here is E equals h nu. So I know this looks like a V, but this is technically nu. Looks like a V, but that's the Greek letter nu. That's for frequency. E stands for energy, and then h is Planck's constant. So energy is going to be measured in joules. We're familiar with that. Frequency is going to be measured in hertz. Hertz is basically an inverse second. So if I say this happens, at a frequency of 1,000 hertz, it means the wave passes 1,000 times per second. Okay. And then lastly, Planck's constant, I'm hoping I've got it. Yeah, I've got it down here. It's joule seconds is the unit, and it's 6.626 times 10 to the negative 34. Very tiny number. That is on your equation sheet. So all three of these equations are on your equation sheet, but you definitely want to memorize them. So the big kahuna is E equals h nu. It tells us that energy of light is proportional to its frequency. If my frequency is bigger, then the light is going to have more energy. If my frequency is really tiny, I'm going to have not much energy, right? So a direct relationship. The other key one is C equals nu times lambda. C equals, well, I usually do lambda nu. So C is the speed of light. I've got that down here. Hopefully some of y'all are familiar with that already. That value, again, is a constant given to you on your equation sheet, but it's 3 times 10 to the 8th meters per second. That's how fast light moves. And then lambda is wavelength. So this guy right here is going to be measured in meters. Now, when we see here, the relationship between, C is a constant. We don't really care about it necessarily. But the relationship between frequency and lambda is inverse, right? If their product equals a constant, that means if one goes up, if frequency starts getting really high, the wavelength of that light is going to be lower. If the wavelength goes up, the frequency of the light is going to need to be smaller. And then we can also do a little substitution to say, well, could I replace, the nu term in E equals h nu? Could I just replace it with C over lambda? And totally, you don't have to memorize this iteration or be super familiar with it, but just, you've got this pool of basically three variables, E, nu, and lambda, right? And then you've got two constants, C and H. So these are constants and these are variables. So knowing how they relate to each other qualitatively, definitely something worth, kind of committing to memory, but also you can work it out if you can just look at the equation, the base equation, and say, okay, well, that's a direct relationship between E and nu. This is an indirect relationship between nu and lambda, so on and so forth. Okay. Now, I mentioned that photoelectric effect. That is when you shine energy. So we've got this in the diagram, right? This is the energy we're shining in, and then it hits an electron, and it can eject the electron, right? If it gives it enough energy. There is a specific amount of energy that is needed to do that. We call this the binding energy of an electron, right? And it tells us ultimately how tightly that electron is held to the atom. Right? So if there's not much binding energy required, that means I can shine a very weak light on an atom and its electrons just fly off. But if the binding energy is really high, that means that electron is held really tightly and it requires a lot of energy zapped into it. Now, because of that, we can make some connections between things we already know about atomic structure, like when an electron is closer to the nucleus, or that nucleus has a higher positive charge, so something with 20 protons as opposed to 10 protons, the binding energy for those electrons is going to be greater because that effective nuclear charge is greater. So all that stuff is that's like unit 1 periodicity stuff. Definitely worth a review for how we think about those qualities of atomic structure. We can also think of that binding energy in terms of the frequency associated with it. So recall we've got E equals h nu, right, for a specific binding energy, right? Let's say the binding energy for this electron was 1 times 10 to the negative 10 joules, okay? Well, then I could solve for the frequency, right? Because h is just a constant. And that is known as the threshold frequency. So when we think about like, hey, I need to shine this light on, an atom to eject its electron, I don't say like, all right, cue up the negative 10 to the negative 10 joule light source. We don't really like quantify light that way. We don't categorize light in terms of its energy primarily. We primarily categorize it in terms of its frequency and its wavelength. So the threshold frequency it's just a little more useful when we think about selecting different kinds of light as well as wavelength. So this blue one right here, because the waves are passing more quickly, this is a higher frequency, and this is a lower frequency because the waves are passing less regularly. If we think about each peak sort of passing every second, this one has a lot more passing every second than the one on the left. And we can see represented here that the higher frequency over here is exceeding the binding energy. The one in the middle is exceeding the binding energy. The one on the left is not exceeding the binding energy because it's got that lower frequency, which is related. Then you aren't going to get those electrons ejected. Okay. So we talk about threshold frequency, we've also got a corresponding wavelength max or threshold wavelength. So again, if I can go from the E binding to the threshold frequency, well, once I find that value, right, recall we have an equation that goes between wavelength and frequency, right? So now we've got this guy and this guy, and if I found the threshold frequency, then I can just rearrange this and say, okay, well, wavelength max equals the speed of light, c divided by that threshold frequency, which I can calculate given the binding energy because h is a constant. So again, why is this useful? Because we often categorize different kinds of lights. I mean, you'll see in our Beer's Law lab we do by the wavelength, right? I've got a little knob that says, hey, this light is 600 nanometers. This light is 800 nanometers. So it's just a common way we think about it. And again, the wavelength is literally the length of a wave. So the distance between this peak and the next peak. That's the wavelength of this light. This blue light is much shorter in wavelength, right? 680 nanometers to 420 nanometers. So the wavelength for this, the distance from this peak to this peak. So a much shorter wavelength, right? But again, a shorter wavelength means a higher frequency. So this blue light is going to be ejecting electrons more successfully than this red light. You can see no electron ejected here, but we do for the green and blue. With shorter wavelengths, you get higher frequencies and thus higher energies. So this is a really key takeaway, the direct and indirect proportions of these terms. I'm just going to ask you to read that, but let's go ahead and do some math. Let's see. Okay. So we're given a metal surface. It's exposed to light. We first see electrons being ejected when energy meets 3.3 times 10 to the negative 19 joules. So this right here, that is our binding energy. Great. First question is, what is the frequency of light with that energy? Okay, well, I know energy equals h times frequency, nu. So if I rearrange that, I get the frequency equals energy divided by h. So that's going to be my energy, 3.3 times 10 to the negative 19 joules, divided by my Planck's constant, which is, again, on your equation sheet, 6.626 times 10 to the negative 34 joule seconds. And we'll get whatever that is, 3.3, so 4.98 times 10 to the 14th. 98 times 10 to the 14th. Now, recall that the units of joules cancel out, so you're left with the seconds on the bottom. So you could put units of seconds to the negative 1, or you could say hertz. Those are equivalent units. So how many waves pass per second, right? It's a very high frequency. Now, what is the wavelength for light? Well, now we're going to think about our equation that relates frequency with wavelength. So that's c, the speed of light, equals wavelength times frequency. So rearranged, we get wavelength equals c over frequency. Speed of light is 3 times 10 to the negative, or to the positive 8, excuse me, meters per second. And we are dividing that by the value we just got for frequency. So 4.98 times 10 to the 14th. And we will see what we get. So 6.02 times 10 to the negative 7. Negative 7. And notice the units that cancel out, we're going to get seconds, seconds, canceling out. These are just going to be meters, right? So that is our wavelength. Let me write that there. This is our frequency. And the last question, what's the color of this light? Well, we're given all these wavelengths in nanometers, so we'd have to convert meters to nanometers, which basically means, what is it, times 10 to the 9th? Yeah, so 1 meter to turn it into nanometers, get 1 meter is equal to 10 to the 9th nanometers. So if I turned this into nanometers, this value would become 602 nanometers. Okay, so which category of light is that in? That's going to be orange light, right? It's between 590 and 620. So it's orange. Yahoo! All right, last question. Copper sulfate solutions absorb light at a wavelength of 635 nanometers. Calculate the approximate energy of 1 photon of this light. Okay, so now we're going basically in the reverse direction. We've got wavelength. We're going to go from wavelength to find frequency from that speed of light equation. From frequency, we're going to find the energy from that E equals h nu equation. So let's look at it. We've got C equals lambda nu rearranged to find the frequency. It's nu equals C over lambda. So C is still the same old 3 times 10 to the positive 8 meters per second. But here we have to pay attention to units, right? I'm given a wavelength in nanometers. I want to have to convert that to meters, and it will end up being this many meters, so that the units play nice. I suppose you could convert the speed of light into nanometers per second, but that sounds stupid. So, 6.35 -7? Yeah. So we get 4.72 times 10 to the 14. 2 times 10 to the 14th, and that is again our per second, right? Our frequency value. So for this guy, we are using the equation E equals h nu. We've just solved for nu. So I'm putting in Planck's constant for h, joule seconds, and then I'm multiplying that by 4.72 times 10 to the 14th per seconds. And that'll give me an answer in joules. So let's see what that gives us. 6.66 times 10 to the negative 34 times 4.72 times 10 to the 14th. So 3.13 times 10 to the negative 19. 10 to the negative 19. That's joules. That would be our answer. Not too bad. Really just some equation algebraic manipulation. Hopefully it feels okay. There's some stuff we can do in here with like per moles, some stoichiometry, and that is not too bad. One more lesson.